One really important concept when we talk about solutions is the idea of discussing the concentration of the solution. Now, concentration is just a measure of how much solute is dissolved in a given amount of solvent or a given amount of total solution. There are a lot of different ways of measuring that. We could be verbal about it. We could say that a solution is either dilute or concentrated. And a dilute solution would be one that has a relatively small amount of the dissolved solute, where a concentrated solution would have a relatively large amount of dissolved solute. One place you might have kind of heard that terminology is in looking at the grocery store at juice, fruit juice. If you go to the freezer section and you buy a little can of apple juice, you buy apple juice concentrate. And that apple juice, they took apple juice and they boiled it down so that the water would be removed and the sugars and flavors, which have a higher boiling point because they have stronger intermolecular attractions, then do not boil off and you get a concentrated juice. That's why when you make juice from those little containers in the freezer section, you have to add water. You don't just drink it directly once it's defrosted. That is juice concentrate. It has a relatively large amount of that sugar and flavor for the small amount of water still in there. The problem with dilute and concentrated is that that's very relative. Who's going to say what relatively small is? Is that 1 mole per liter? Is that half a mole per liter? Is that 1 part per million? Is that 1,000 parts per million? There's a lot of different ways of measuring concentration. And so using a very relative term like that is not super helpful. So what we generally use as academic chemists in high school is the concept of molarity, which is a unit we have seen before. In fact, we did just use in our acid-base calorimetry lab, we used the fact that we had a 1 molar solution to determine how many moles of sodium hydroxide we had reacted. So remember that molarity, big M, stands for moles per liter, or even more often millimoles per milliliter, because we are very rarely doing things on liter scale in an academic lab. And so one thing we could think about if we are looking at molarity, big M, is the molarity the same if I use moles per liter or millimoles per milliliter? So let's try and see. Here I have 1.0 big M. Oftentimes the big M is italicized. I know that big M stands for moles per liter, so that tells me I have 1 mole per 1 liter. So let's see what happens. Well, the first thing I would need to do is I would need to change my mole into millimoles because I want millimoles per milliliter. So that would put the mole on the bottom and the millimole on the top. There my moles would cancel out, and that would give me millimole per liter. But I want millimole per milliliter, so I'm going to need to put the liter on top to cancel my liter on the bottom. And 1 liter is 1,000 milliliters. And so look what happened. I just multiplied by 1,000 and then proceeded immediately to divide by 1,000. And 1,000 over 1,000 is just 1. So just like using milligrams per millimole for molar mass, the number for molarity does not change as long as I use millimoles and milliliters. I often say the milli on the top cancels the milli on the bottom. So this is a really important concept, and we're going to use this mole per liter unit kind of as a conversion factor or a formula to be able to move between volume and moles pretty often. So let's try a practice problem here. I have 3.50 liters of solution that contains 90 grams of sodium chloride. What is the molarity of that solution? Well, the first thing I want to do is I want to figure out what am I looking for. And I'm looking for big M, molarity. And big M molarity is moles over liters. I have liters. I have 3.50 liters. But this is not gram-larity. So I need to take that 90 grams of sodium chloride and convert it into moles so that I can put moles over liters. So of course that would require the molar mass of sodium chloride, which would just be adding up one sodium and one chlorine. That gives me about 58.44. So in order, of course, to get my grams to cancel, I would have to put the gram on the bottom and the molar mass up top. And that gives me 1.54 moles of sodium chloride, which I think about it makes some reasonable sense. 58 is pretty close to 60. Half of 60 is 30. So 60 plus 30 would be 1.5, and that'd be about 90. So since it's a little less than 60, it should be a little more than 1.5 moles. And it is. So now I just need to finish up and answer my question. I have a number of moles. I have a number of liters. So we just put the moles over the liters and do a little division problem. 1.54 moles divided by 3.50 liters gets me 0.440 big M. I could do this as a conversion factor. I could say 1.54 moles in 3.50 liters equals X moles over 1 liter. But in fact, I'm going to end up in exactly the same place. I just end up with dividing the moles by the liters. That gets me the big M molarity. The biggest thing here is recognizing that we did have to turn that grams into moles. So here's another really common way of applying molarity, and this is exactly what we did in our acid-base calorimetry lab. In this case, I have a volume and I have a molarity, and I want to find out how many moles of HCl was in that solution. So if I think about the fact that big M is equal to moles over liters, then I can actually find a relationship here. I can solve this equation to get moles by itself. I'd have to multiply both sides by liters to get moles by itself. So molarity times liters is equal to a number of moles. And this is an incredibly common and incredibly useful relationship in AP chemistry, and even more so if we think about using molarity and milliliters so that we can get into millimoles. And then we can use some numbers which don't have quite so many zeros out front, which, is always nice. So I know I need to take the molarity, 0.5 molar, times the volume, 0.8 liters. So if that's 0.5 molar times 0.8 liters, I get 0.4 moles. Okay. And again, I like to think about the fact, does this make sense? That is not quite a liter. It's a little less than a liter, so I should have a little less than half a mole. A whole liter would have half a mole. So less than half a whole liter will have less than half a mole. Both of these numbers do have one significant digit, so I just end up with one significant digit in my answer. The 4 in 0.4 is my one significant digit. This is just an incredibly important and common relationship. Please make sure that you write that down with a star next to it. We are going to use it a lot coming up in some of our next units, and certainly a lot next year. So let's do 2 more example problems, and I'm going to have you go ahead and pause this. I'm going to have you try the problem, and then we will look at them. So hit pause and try thinking through these problems, and then we'll go over them. Okay, so hopefully you tried these out. I see an issue with this first one. The issue I have with this first one is I have millimoles and I have liters. And I know that looking at my molarity formula, it is either moles over liters or millimoles over milliliters. So I really have to be consistent. If I'm going to use the 0.25 liters, I need to change that 10 millimoles into moles. If I'm going to use 10 millimoles, I need to convert that 0.25 liters into milliliters. Okay, so if I have molarity as millimoles over milliliters, and I want to use millimoles, I'm going to have to make that into milliliters. That moves the decimal place 3 times. 0.250 liters is 250 milliliters. So I'll set this up as 10 millimoles over 250 milliliters. That gives me 0.0400 molar. And I did put those 2 zeros on at the end for a reason. I had 3 significant digits in both of these, 10.0, there's 3, and 250, that is 3. So I needed to have 3 significant digits in my molarity. Since leading zeros do not count, it's 400 are the only 3 significant digits here. So how many grams of potassium permanganate are in a 750 ml volume of 0.050 molar solution? Well, I don't have a way to get directly to grams here, but I do know that I can get myself to moles, and then I can use the molar mass to get to grams or milligrams. So I remember that molarity is moles over liters. So molarity times liters gives me moles. Of course, right now I am in milliliters. So if I want to work in moles, I'm going to have to change that 750 milliliters to liters. And that's going to move the decimal place 3 times. It's going to be 0.7500. And then once I'm in moles, I can use the molar mass to get into grams. So first things first, let's get to moles. I take my 0.750 liters, and I really probably should have put an extra 0 on here, but I only actually have 2 significant digits here. So I'm going to do that and multiply these together. That gets me 0.0375 moles. I hang on to an extra sig dig here because I'm not completely done. And then I'll go ahead and multiply that by the molar mass. And then I'll go ahead and round to my 2 significant digits from my molarity only having 2 significant digits. So I multiply by my molar mass so that my moles will cancel, and I get 5.9 grams of KMnO4 potassium permanganate. So one of the most useful skills now that we know about molarity is handling dilution problems, changing the molarity of a solution, usually making it less. And the reason that's so very useful is that most solute things that you can buy in solution, like acids, for example, are distributed in concentrated form from the manufacturer. And usually that concentrated form, which is the most effective for shipping because water is heavy. So the less water I have in my solution, the more effective it is to ship because I'm getting more of my actual active ingredient. So for example, with hydrochloric acid commonly comes as a concentrated 12.0 big M solution, 12 moles per 1 liter. And that's, again, we would call that 12 molar HCl. That means that this is a very, very concentrated, very strong, and very dangerous solution. 12 molar hydrochloric acid, when you open it, will literally fume hydrochloric acid vapor into the air. So you don't want to open it and then stand around breathing nearby. It's very strong and it's very dangerous. So I wouldn't necessarily want to use that for every day in the lab. Now, I could buy a 1 molar solution of HCl. I mean, that's what we used in our acid-base calorimetry lab. We had lots of 1 molar HCl, and I could have bought it directly from Flynn, but the problem is, one, not everything needs 1 molar acid. There are lots of things that we've done this year that needed much less than 1 molar acid. And two, like I said, water is heavy. So if I want to ship hydrochloric acid solution, actually most of what I'm shipping right there is water, and I can get water for free out of the tap at school. So if I need lots of different concentrations, or if I don't want to pay a lot of money in shipping charges, it's best to know how to dilute them myself. So why can't we use concentrated acid for every application? Here are several options. Why don't you see which ones you think might be correct? If the amount of acid needed in an application is very small, because we have a very concentrated solution, so we need a very small volume to get that number of moles, it might be difficult to measure a very, very small volume. Using too much acid might be impossible to reverse safely, or if I use too much acid, it might cause an unexpected effect. Concentrated acids are pretty hazardous. That might not be something that I want out for a lot of applications. So what of these answers do you believe is correct? Well, if you said all of the above, exactly, all of the above. For example, let's say I only needed 10 millimoles of hydrochloric acid. If I only needed 10 millimoles of hydrochloric acid at 12 molar, I would need less than 1 milliliter of acid. And that is pretty difficult to measure very accurately using most of the equipment that we have in our high school lab. I mean, there are certainly ways to do it, but they're certainly very expensive, very specialized equipment that it might not be very cost effective or useful to have in this lab. On top of that, like I mentioned, some of these concentrated acids will literally fume into the atmosphere. So I really don't want to have a beaker of 12 molar acid sitting out. And I certainly don't want to have a beaker of 12 molar acid sitting out, because if it gets on you, you have a very, very short window of time before you get serious skin damage. This is the point, if I were in the room, I would show you where last year, filming a video for my AP class, I got 15 molar nitric acid on my arm. And I have a scar now where I literally burned my skin and damaged my skin because I didn't realize that I'd gotten the acid on myself. And by the time I realized it and got to the sink and rinsed it off, I had a pretty good sized wound on my arm. So concentrated acids are hazardous, and I would really like to be able to not use acid that I have to be terrified having in a room full of students. So let's think about this. First, is the concentration of this solution in my graduated cylinder the same in all of these basic, let's say about 10 milliliters of solution? And the answer, of course, is yes. A solution by definition is homogeneous. It is the same throughout. So all of this is going to be the same throughout the whole container. That's why it doesn't matter whether I pour directly from the bottle or we have a refill later. As long as I'm using a solution from the same overall container, the concentration should always be the same. Is the concentration in millimoles per milliliter the same as in moles per liter? Again, yes, we proved that earlier. But again, if we think about it, this is just a matter of multiplying or dividing by a particular fraction. If I have 2 moles of solute in 1 liter of solution, well, then I have 0.002 in 0.001. You can see how that would simplify to the same fraction, and that's 2 millimoles in 1 milliliter. So the solution is 2.0 molar either way. So let's say that for a student experiment, we need 2 liters of hydrochloric acid that is 0.0250 molar in concentration. But what I have in my stockroom right now is 1 molar. So how can I take this 1 molar solution and figure out how much water I need to add to dilute it to be 0.250 molar? So I need 2 liters of 0.025, and I have 500 milliliters of 1 molar. Well, what's really going to be the key here is that the millimoles of solute in the concentrated and dilute solution are going to be the same, because all I am doing when I dilute a solution is adding solvent. I am not adding solute. I'm always adding solvent. So the millimoles of solute at the beginning has to be the same as the millimoles of solute at the end. And I know that the millimoles are molarity times liters. So I can figure out how many millimoles I would need in my dilute solution. I take my molarity times my milliliters. That's 50 millimoles. And I say to myself, how much 1 molar solution do I need to get 50 millimoles? I get that 50 millimoles from the concentrated solution. So that 50 millimoles, well, if it's 1 molar, every 1 milliliter has 1 millimole. So if I need 50 millimoles, I need 50 milliliters. So then that would tell me how much of my more concentrated solution I need. So how would I go ahead and actually go about making this solution? Well, I would measure out 50 milliliters of my 1 molar solution. And then I would remember that I always want to add acid into an amount of water. We never want to pour water into a concentrated acid because the solution is going to get quite hot when we actually do this. So if we pour a small amount of water into a more concentrated acid, we're actually going to end up quite possibly making it so hot that it will steam. So there's an old saying, do as you oughta, add acid to water, because you always want to add that acid into a larger amount of water so that the larger amount of water, remember water has a freakishly high specific heat capacity because of that hydrogen bonding, making it difficult to get the water molecules moving faster and faster. So we want to let that larger amount of water soak up the heat and not turn into steam or vaporized hydrochloric acid. So we would start, say if we need 2 liters, we might start with a liter of water or 500 milliliters of water. We would add the acid, let it cool down, and then we would go ahead and add the water up to the 2-liter mark. So you always want to add acid to water because of the heat generated by that solution. And I can tell you, if you are doing this with a very concentrated solution, for example, when I do an AP titration, at one point I need to dilute our think it's 16 molar sulfuric down to 3 molar sulfuric. I'll do that in the morning, and second or third period, it will still be warm to the touch. So it really can generate a lot of heat. So essentially, here's a quick version of that formula, and it goes right down to the fact that millimoles at the beginning, or moles at the beginning, is equal to moles at the end. Molarity times volume is moles. Molarity times liters is moles. Molarity times milliliters is millimoles. So the molarity times the volume that I start with, that gives me a number of millimoles I start with. And it has to be equal to the number of millimoles that I have at the end, the molarity times the volume at the end. So our M is our molarity, our V is our volume, and that is going to be our total volume at the end, and our total volume that we measure out to begin with. And that volume can be in milliliters or liters. You just have to be consistent. So let's take an example. I have 500 mils of 6 molar solution, and I need to dilute that to be a 1 molar solution. So what is the final volume of my solution? And it really doesn't matter whether you set up the numbers as M1 or V1 or M2 or V2, you just have to be consistent. So I know that that 500 milliliters, whether I call it V1 or V2, has to stay with the 6 molar, the 6 big M. And that it's most important that they stay together. So what I'm going to do is I'm going to look at that and say, oh, dilution problem. I know the formula for that. M1V1 equals M2V2. So I'm going to write it. Then I'm going to, you guessed it, solve it. So I'm going to call my V2, what I'm looking for, final volume is usually V2. So I've got M1, 6.0 molar, V1, 500 milliliters, and M2, 1.0 big M. So I'm going to plug that in. 6 molar times 500 milliliters over 1 molar. Notice my molarities on the top and the bottom will cancel out, and I get 3,000 milliliters of total solution. Or I could make that 3 liters of total solution. Since I have only 2 significant digits, I might change that to 3.0 liters to make it a little easier to round. Let's take a moment to look at that total solution volume. What if I ask this a slightly different way? I have 500 milliliters of a 6 molar solution. I need a 1 molar solution. How much water do I need to add to make this 1 molar? Well, I've still got exactly the same problem. I'm going to write it, solve it, math it. I have 3,000 milliliters of total solution. But here's the thing. Do I need to add 3,000 milliliters of water? Let's read the question. Okay. Notice this is my total solution. So 500 mils of that total solution is going to be from this 6 molar solution. So in fact, I don't need to add 3,000 milliliters of water. If I added 3,000 milliliters of water, I would have ended up with 3,500 milliliters of total solution, and it would be too dilute. I actually only need to add 2,500 mils of water, because 2,500 plus 500 gives me my 3,000 milliliters of total solution. So that V2 is not the amount of water I need to add. V2 is the total amount of solution that I'm going to get. So one other really common way of dealing with concentrations is by looking at what's called a mole fraction. And mole fractions are just fractions like every other fraction has always been. If I have a dozen donuts and 3 of them have chocolate icing, I would look at that and say, 3 of those 12 donuts have chocolate icing. That fraction is 1 over 4.25. Okay, this is exactly the same thing. So the mole fraction, which we signify as X, big X, capital X, is the number of moles of one component of the mixture. What's the part I'm interested in? Donuts with chocolate icing, divided by the total number of moles of all substances present. So the total number of donuts, whether they had chocolate icing or plain or jelly filled. So moles of what you're interested in over the total number of moles. That's the mole fraction. This is very, very common, and it's very, very helpful also when we talk about gases, because mole fraction is a way to get to the partial pressure of a given substance, because the number of moles of whatever is in a gas, the number of moles of that component of the mixture is the number of molecules bouncing off the walls and the ceiling and the floor. So that is the fraction responsible for that fraction of the pressure. So here's an example. 0.1 moles of sodium chloride is dissolved into 100 grams of pure H2O. What is the mole fraction of NaCl? Well, I know mole fraction is the number of moles of sodium chloride over the number of moles of everything. So that means I've got a little bit of a problem here. I don't have a number of moles of water. I have a number of grams of water. So I have to remember, again, this is not a gram fraction. This is not a molar mass or something weird like that. This is a mole fraction. So moles on the top has to cancel moles on the bottom. Fractions should be unitless when they need to compare the same things. So I would convert my grams of H2O into moles of H2O using the molar mass. 100 grams of H2O is 5.551 moles of H2O. And I'm not going to put 5.55 on the bottom of my fraction because it said total moles. So that means I have to add the moles of water and the moles of sodium chloride together. That gets me 5.651 total moles. And now I can actually go ahead and calculate my mole fraction. So I'll put my 0.1 moles of NaCl on the top and my 5.651 moles on the bottom. That's 3 significant digits from 100 on the mole of NaCl. So I get 0.0177, and that is unitless because mole over mole is unitless. If you aren't about to end up with something unitless, you are not doing your mole fraction correctly. So here's one more example problem. And again, I'd like you to try pausing it and then going ahead and trying it again. So here's your problem. You have a solution which contains 4.8 grams of sodium chloride and 7.2 grams of potassium bromide in 76 milliliters of H2O. What is the mole fraction of sodium chloride and potassium bromide? Again, I'm going to give you a second to pause this and try it, and then check your work. All right, well, it's not a gram fraction, and it's not a milliliter fraction, it's a mole fraction. So the first thing we're going to have to do is convert these things into moles so we can find our total number of moles. So first we're going to take our 4.8 grams of sodium chloride. We're going to divide that by the molar mass of sodium chloride, which is 58.44. That gets me 0.082 moles. Then I'm going to also need to get that 7.2 grams of potassium bromide into moles, which is again fairly straightforward, 7.2 grams. We'll divide it by the molar mass, 119.002, I believe. And so I get 0.061 moles. But I still can't just add those together because there's still water involved, and water is a thing and it has moles, so we have to add those in too. Now my problem is 76 milliliters is not a thing that I can directly cancel with the molar mass of water. But I do remember that water has an extremely convenient density. So if I remember that 76 milliliters of water can be converted to grams because the density of water at room temperature is essentially 1 gram per milliliter, that'll get me into grams of H2O. And then I just divide it by the molar mass of water to get into moles. So to get the total number of moles, I would just need to add all three of these numbers together. I only have 2 significant digits. So, and also, since I only have 2 significant digits, I can really only have 1 decimal place here. So 4.2, add those other 2 in, and I get a total of 4.4 moles. And that's going to be the denominator of my mole fraction for both NaCl and potassium bromide. So let's go ahead and use that and we'll get our mole fractions. So for the mole fraction of NaCl, I'll take the moles of NaCl over the total. 0.082 moles over 4.4 moles. Again, moles cancel moles, so I get a unitless number, 0.019. And for my potassium bromide, I'll take moles over moles, and that will give me 0.014. So that's a brief update on how do we calculate mole fractions, how we do dilutions, how we do molarities. We'll do some practice on this next week, but make sure you are keeping up with your notes, and I will see you again soon.